можно начинать. Что пока непонятно, по какому языке говорить. Не, ну да. Давайте я пока по-русски буду говорить, я писать по-английски. Значит, мы в прошлый раз обсудили, что... Что мы вообще делаем? До конца семестра мы обсуждаем вот это соответствие, что вот алгебра Ли G полупростая на C, H это максимальная торическая, и мы построили соответствие, что это мы сопоставили систему корней, еще не совсем, вот сегодня мы наконец-то это соответствие построим, точнее наоборот, Фи это система корней. Это евклидово пространство, да, это. То есть мы построили соответствие между алгеброй Ли. Ну, пока вопрос. То есть в прошлый раз мы доказывали теорему вполне приводимости, потому что мы ее использовали для построения, там везде построение с L2 использовали. Так что теперь мы хотя бы каждой паре алгебра под алгеброй мы можем сопоставить уже по-честному систему корней. Да. Не просто фи, а пара, потому что система корней это не просто множество конечное, а подмножество в евклидовом пространстве. Не вижу никакого противоречия. Построили евклидово пространство, мы построили два объекта евклидового пространства и систему корней в ней. Потому что систему корней просто построить без евклидового. Сначала надо построить евклидово пространство, чтобы вообще про корни говорить. Заложено, да, что система корней это подмножество евклидового пространства. Так что сначала надо построить евклидово пространство, потом в нем подмножество. Okay, so we constructed. We already know that for any pair of Lie algebra and maximal toric subalgebra, we can construct root system. However, it's not clear. Today we will not prove, but again I will leave some lemmas as exercise. I will put in lecture notes. But today our purpose to prove that this correspondence is indeed map, so it does not depend on maximal toric subalgebra. So you can choose semi-simple Lie algebra and any maximal toric subalgebra, and any root system you obtain here will be isomorphic. So this does not depend on choice of maximal toric subalgebra. Then we will obtain map from semi-simple Lie algebras to root systems. Because now we have map like this from pairs. Yeah. So if you consider set of pairs, semi-simple Lie algebra and toric subalgebra, then we have root system. But we want to project onto this component. It follows from the following fact, which is important by itself. It's called its theorem. Theorem. Okay, I need to define something before it. So let's define some group. Let's recall that. Okay, let's consider group G, where G is given by the following. G is as follows. G will be subset of automorphisms of our Lie algebra, and we define it as follows. It's exponent of add x, where x and G, and add x is nilpotent. So we discussed it, as I remembered. So add x is is derivation of Euler algebra, right? So e to the power add x is automorphism of Euler algebra. E, it's like ordinary, it's nilpotent operator, you do not need any topology here, it's well-defined thing. And if you consider derivation and exponent of derivation, it will give you automorphism. Did we discuss it? For any nilpotent, not local, for any nilpotent. If add x is nilpotent, then it's always automorphism of Euler algebra. Okay? And like it's obvious, it's just polynomial, right? For any concrete element, if you want to apply this to element of Euler. So the claim is that it is indeed automorphism. So I hope as I understand we discussed it at some point, maybe on seminar. If not, so I can leave it as an exercise. It's simple thing. So, but now it's automorphism, and you could apply it to any element of G. Okay. So theorem for any two toric subalgebras, maximal toric subalgebras, there exists some element sigma from G such that sigma of H1 is equal to H2. It's ordinary. It says that any two Cartan subalgebras are conjugated because for classical groups this automorphism is just conjugation by some matrix. But in principle it's not necessary. So this is Chevalier's theorem. But okay, could you say me how from this theorem it follows that it does not depend on your maximal toric subalgebra? So we know that there's an automorphism of Euler algebra such that it maps H1 to H2, and H1 and H2 are two. So if you have two toric subalgebras, you have decomposition like this, right? From H1 star G alpha, and at the same time you have G is equal to H2 plus G alpha, okay, let's say G beta from H2 bar. Okay, and we have automorphism which such that sigma of H1 is equal to H2. Okay, but in principle, but let's unwrap this. So here you have some functions on H1 star. Here you have some functions on H2 star. These guys form some root systems. These guys form some root system. So here you have killing form. Killing form is the same, right? But you restrict your killing form to H1 or to H2. It's like, in principle, it's different. So what we want to say, in principle, we need to define what are the same root systems, right? What does it mean? Probably when two root systems are isomorphic. So so we can give definition, but what do you think? So it should be some map. So you have E1 phi1 and e2 phi2. It should be some map, linear map, from e1 to e2, such that what? So it's linear, it's bijection for sure. So you mean that phi f of phi1 is equal to phi2, but is it enough? Is it orthogonal map or not necessary? But what could be different? We can say that f is c times some g, where c is greater than 0, some number, and g is orthogonal. No, because if you have root system, you can multiply by some number and consider some dilation, and it will be the same root system. And it's a little bit unmotivated. We will see that it corresponds to isomorphism of Lie algebras like next time. But in principle, we should say something like this. Okay, so here you have Killing form restricted to some. So how it's constructed? We restrict Killing form to q of h, q of phi1 to this, right? So consider such space. We restrict Killing form to phi1, so we prove that everything is rational, and it's positive defined. Here you have q to r. So we want to say that root systems are isomorphic. So we want to construct map between these Euclidean spaces. Do we have such map? How to construct how to construct isomorphism of root systems? So, we know that if you consider sigma, you restrict to h1, right? So sigma maps h1 to h2. So sigma is map. So you could consider sigma as map from h1 to h2. Right? Okay. Does it probably, is it true that it preserves Killing form? If it preserves, then it's enough. So it's isomorphism between h1 and h2. So our Euclidean space constructed by means of a restriction of Killing form to h1 to h2, it then restrict to some real subspace. So how Killing form is defined? How we define Killing form? What is Killing form? It's trace of ad x, ad y. And you have such map. And it's isomorphism. So if you want to compute, if you have h prime from h1, then h prime is equal to trace of ad h prime, right? But let's see. So the question is it true that automorphism of your Lie algebra preserves Killing form? Like some simple question. If you have automorphism of Lie algebra, maybe it's okay. G is Lie algebra. You have automorphism of it. F, right? And you have Killing form of x, y. You have Killing form of f of x, f of y. F is automorphism. So this is trace of ad x, ad y. This is trace of ad f of x, ad of y, f of y composition. Then what? So here. are these traces the same? So what you want to say is that add f of x. If you apply it to y, you get what? It's like f of x, y, right? Here you have, so you have like product of two matrices, big matrices. F of what? Okay. So it's f of, it's composition of f with what? With minus, it's like minus, right? Because add on the first, add, you want to say it is f with add x, so we apply to y, okay, yeah. Okay. And f minus 1, okay. So now it's clear, because it's just conjugation, trace is invariant and the conjugation, so you here in the middle it will be. Very good. Therefore, our automorphism preserves Killing form, therefore here it's also, it will give you some map from this Euclidean space to this Euclidean space. Like it will be better. It will be not C times, it will be not C times something, it will be just literally orthogonal. Very good. So we have some map from E1 to E2, and y, if f of V1 is V2, if you apply sigma to this, if you have G alpha, what is sigma of G alpha? It was f. So G, what is G alpha? G alpha is the space of x from G such that hx is equal to alpha of hx. We want to consider sigma of G alpha. What we can say about sigma of G alpha, how elements from Cartan subalgebra, from maximal toric subalgebra acts on elements x. So sigma of G alpha, like sigma of x, such that x from G alpha. What we can say about action of h on sigma of x? So if I want to act x on sigma of h, sigma of h, h act by h on sigma of x, what we'll get? It's again, right? So it's just commutator. We already did it, right? It's ax. It's like sigma of what? Of sigma minus 1 of h x, right? So it means that, but roots, it means what? But h, I'm sorry, so h should be, so we have two h's. So here you should consider h from h2, right? So I want to see what I want to consider sigma of G alpha and how H2 acts on this sigma of G alpha. And I want to say that it is it acts by some linear function, or then you obtain what you want. But okay, let's see. So I want to consider h from H2, sigma of x is sigma of sigma minus 1 of hx. It is as, now it's from H1. it acts by alpha, some alpha, so it's equal to sigma of alpha of h x. It is by sum, it's alpha of h sigma of x, right? Oh, but it's strange, a little bit. Where? Here. So it will be alpha composition with sigma minus 1. Okay. So I see that if you consider image of G alpha, it will be G alpha sigma minus 1 composition. So we see that it works in this direction. So all these guys maps to these guys, all these guys maps to these guys. Do we see that f of phi1 is phi2, so f of phi1 is contained in phi2, f of phi2 is contained in phi1, but it is isomorphism, so it's bijection. So f of phi1 is indeed phi2. Okay, so it means that isomorphic, it means that this theorem is exactly what we want. Okay, exactly what we want. So in order to prove it, we will prove in greater generality, we will prove it. We will give another characterization of maximal toric subalgebras, which is called Cartan subalgebras for any Lie algebra. So let's give definition. Definition. Let G be. Okay, let me write any Lie algebra. Any finite dimensional Lie algebra. H from G is called Cartan. It's called Cartan subalgebra. If, first of all, H is nilpotent, and secondly, H is equal to its own normalizer inside G. So normalizer, what is normalizer? It's a set of elements from G such that XH belongs to H. So normalizer by its name, it's maximal subalgebra such that H is ideal in its normalizer. So it comes from group theory, because in group theory you have normal subgroups. Here it's still normalizer, but it's like a little bit strange that it's normalizer, but it means that H is ideal in normalizer. But okay, so this is called Cartan subalgebra. What I want to and we will prove any two Cartan subalgebras are conjugated. So so I reformulate this theorem for Cartan subalgebras. And what I want to say is that maximal toric subalgebras are Cartan subalgebras. Let's see. So I claim that any maximal toric is Cartan. Any maximal toric subalgebra is Cartan subalgebra. So in semi-simple Lie algebra. So it's obvious. Is Cartan. I will say. I just write it because it's important. Why? So we want. We have an abelian subalgebra, so it's obviously nilpotent. Right? Abelian subalgebra is obviously nilpotent. And we want to consider its normalizer, but what is not so normalizer? So what we already know that If G is maximum authoric subalgebra, then we have such decomposition. Okay. Normalizer is a set of elements such that commutator of X use any element of H belongs to H. Do you know a lot of such elements? We know that if you commute some element from H with some element from here, you get something. You will get what's alpha of H, and you always can find H such that it is not 0. Therefore, because H G alpha is equal to G alpha, it follows that H is equal to its own normalizer. Because it's abelian. By definition, it's a abelian subalgebra consisting of semi-simple elements. Okay, so therefore, in fact, so it will be, let me say, exercise. For example, probably it will be exercise in your next sheet. But in fact, inverse is also true. Any Cartan subalgebra in semi-simple algebra, we don't need it formally, therefore we will not prove. But in principle, that's not bad to know. Subalgebra is Cartan, is maximum authoric. So it's the same. For semi-simple algebras, it's the same condition, like equivalent coefficient. But for us, it's enough to know that any maximum authoric is Cartan. Then, if you know that any Cartan subalgebra is conjugated, then any maximum authoric is also conjugated, are also conjugated. So we will get that root systems are the same. No, I don't think so. We don't need to show that itself. We don't need to show that centralizer is the same. We need to show that normalizer coincide with H. Normalizer is different from centralizer. Yes, that's true. That's true. That's true. Where? Because we use this decomposition. For simple algebra, only H is equal to a centralizer of H. Like it's what is the most non-obvious thing in this decomposition? H is equal to G0, so centralizer of H. That H is self-centralized, and it was the hardest thing to prove. But everything else was pretty obvious. But okay. In order to prove this, so now we want to prove that, and moreover, we will prove it in more general setting. You can define Cartan subalgebra in any algebra. It's not clear why, so it's important, but I'm also not an expert in the theory of arbitrary algebras. But we will prove it for any algebra. In order to prove it, we will use what do you think? What we will use? We will use obviously Zariski topology. Do you know what is Zariski topology? So, and our idea to prove it is to use Zariski topology. In order to do it, we need the notion of regular element. It's also it's interesting by itself. So, definition: let X be element of G. And consider, so it's not definition, okay, let's some consideration before definition. Let X from G, consider add X, and consider its characteristic polynomial. So it's determinant of add X, so of some lambda, let's lambda minus lambda E. It's some polynomial of degree, okay, let's say that, So I want to use the D here. So let's say D is dimension of G plus C D minus 1 minus lambda to the power D minus 1, so on. And the last coefficient is determinant of add x. Okay, so consider a characteristic polynomial of add x. What you could say about determinant? Do you know determinant of add x? It is 0, obviously, because commutator of x with x is 0. So it has kernel, so it is 0. This is 0, obviously. So it's some polynomials, because commutator of x with x is 0. So x belongs to kernel of add x. So it is 0. What I want to say more, I claim that claim CR is some polynomial. What I want, yeah. So another consideration. So let's choose some basis. Let's say x1 xn be a basis of G. Then you can represent any element. Okay, let's say E1, En. You can represent any element as sum on its basis. And you could consider determinant. This x could be different, and then these coefficients depends on your element, right? So C. So it means that A of x is something, and what do you? It's some function on xi's, right? First of all, it's obvious that what? No, not trace. It's polynomial function, yeah. I already said about the Risk topology, so x1, xn. It's some polynomial function on x1, xn. Oh, consider matrix, some big matrix. So. Moreover, probably we don't need this. Okay, so if you don't need, I will not say. Okay, some polynomial function. What xd? Xd. Okay, thank you. It's some polynomial function. Definition. Minimal number R such that CR of X is non-zero polynomial is non-zero. So it is always non-zero. So it's non-zero on G is called. So we know that determinant is 0, right? Some others could be also zeros. We have some minimal coefficient which is non-zero. So it's called rank of Lie algebra. We already have notion of rank. It seems to be completely different. We will see that it's the same. Okay. So I define rank of G as minimal number in this polynomial such that it is non-zero. And if we say that X from G is regular element if CR of X is not equal to 0. So regular element of Ilyin algebra is such element such that CR of X is non-zero. Okay. Yes. No. So C0 of X is always 0 because it's determinant. But some of, so this is non-zero always, this is 1. So we have some minimal which is not identically 0 on Ilyin algebra. So it's just some polynomial function which depends on x. CR of X is not equal to 0. So you have this polynomial. This is you consider for any x, add x minus polynomial, characteristic polynomial for add x. If you choose some basis of Ilyin algebra, then coefficients are some polynomials in this x1, xn. You can substitute into this polynomial your element of Ilyin algebra. So, for example, you substitute in this, you will always get 0. So in next, probably it could be 0, could be not 0. Probably it's also always 0. Probably not, I don't know. And so on. Then you can find the minimal polynomial which is not identically 0. But it still could be 0 on some elements of Ilyin algebra. R is rank of Ilyin algebra, yes. An element is regular if CR of X is not equal to 0. Okay. So let's consider, probably I should consider some example, but we will not have enough time. But let's consider some, it's also like some example, proposition. For example, so rank is some number between what? Rank of G could be number between, it's greater or equal to 1, obviously, because this is always 0. And maximal is dimension of G. Is some number between 1 and dimension of G. And first of all, I want to say that rank G is equal to dimension of G if and only if G is nilpotent. Secondly, I want to say that G is nilpotent. G is nilpotent implies all elements are regular. So it's and third, I want to say that if G is non-nilpotent, then it follows that the set of regular elements is infinite. In particular, we have some regular elements. I can formulate here exercise. Maybe I will see. Maybe we'll did it on the seminar. X, consider G is GLN. Then X from G is regular if and only if it has one eigenvalue a value for one Jordan block for each eigenvalue. For each eigenvalue. For example, its diagonal matrix is regular if it has different eigenvalues, and arbitrary matrix is regular. Arbitrary element of the algebra GL and C is regular if it's in its Jordan form. We have only one block with each eigenvalue. it's some formulation. It's some example. Okay. So proof. Very good. What is characteristic polynomial of ad x if your algebra is nilpotent? I don't. So we have difficulties in this course with directions. Okay, I think in this direction. So if your algebra is nilpotent, then any element is ad x nilpotent. X g nilpotent. Therefore, for any x from any x from g, ad x is nilpotent. So its characteristic polynomial is what? Add x to the dimension. So therefore we'll get rank g is equal to dimension of g. If rank g is equal to dimension of g, then the characteristic polynomial of any element is x to the power dimension. So any element is nilpotent, then by Engel's theorem we have that your algebra is nilpotent. Here I should use Engel's theorem. Yes, two sides. Yeah. Okay, I say by by words proof. Okay, I don't. Okay. So this is obvious. Any element is regular in nilpotent algebra because it's non-zero, because your coefficient is 1, just 1. If G is non-nilpotent, then the set of regular elements is infinite. Why? So what is non-regular element? It means that this CR of x is equal to 0. But it's just some hypersurface in some big space. But you know that hypersurface couldn't be the entire space. Moreover, so we have algebraically closed field. Moreover, it's if you consider this let's say c to the power n minus the set CR of x is equal to 0, it's infinite. So it means that you have infinite number of regular elements. For example, we have at least some irregular elements always. In particular, we have regular elements. Okay. Yes. So you have Jordan normal form of your matrix. And in your Jordan normal form is like, it should be like this. And so on. You couldn't have Jordan blocks with the same eigenvalue. For example, this element is non-regular. Okay. With the same number on diagonal. So okay. Now we need to go back, and probably I will, in order to be able to go to the proof of theorem, I will formulate it as some fact, and then maybe we'll return to this. But it's simple. I want, in order to do in order to proceed to the proof, I need the following thing. Maybe I don't need still. No, I don't need. Yes, I still don't need. Okay, let's prove the following theorem. Theorem is as follows. What is connection? So, firstly, I define Cartan's algebra, then I somehow defined regular elements. Probably there's some connection. Yes, there's some connection. Theorem is as follows. If x from G is regular, suppose that x from G is regular, then one can consider decomposition of G with respect to add x. G lambda x, lambda from C, where G lambda x is the set of x, let's say A. It's a set of x from G, such that what? Such that A x is equal to no, sorry. Kernel of odd x minus lambda e to the power n. It's a generalized eigenspace. You could consider any element of Hilly algebra. You could consider its odd A and consider decomposition of Hilly algebra with respect to the odd A, to its generalized eigenspaces. Корневое разложение with respect to odd A. And the claim is that then G0 is H is Cartan subalgebra. What is what? Some number for some. No, we don't use anything. It's just like Jordan normal form. It's теорема о корневом разложении. Odd x acts on the vector space V. We decompose vector space into the sum of generalized eigenspaces. I claim that G0, zero generalized eigenspaces is Cartan subalgebra in this case. Okay, proof. Now I see that we will not be able to prove this theorem today, but okay, we will prove it next time. We will do as many as we can. Okay, let's denote by V the sum with the sum of generalized eigenspaces with non-zero eigenvalue. Then we can decompose G into the sum of, okay, I need something here already, H plus V. Oh, what I want to say. Okay, lemma. That if you have such decomposition, probably we did it when we prove something about derivations. I want to say that H G alpha belongs to G alpha, and moreover that G alpha G beta belongs to G alpha plus beta. You should be able to prove this by, let's recall that this rule for derivations, Leibniz rule for derivations, right? Add this derivation. We already in fact use this. It's easier to do it considering two derivations. So lemma exercise. It basically follows from Leibniz rule for derivations. It means that H is subalgebra, right? So it implies that H is subalgebra. I don't need so this implies that H is subalgebra. Okay, and now what you know about? Okay, let's consider two subsets. Let's consider set U of elements H from H such that. So what we want to prove? We want to prove that H is nilpotent and self-normalized. We want to prove that, consider subspace add H on H is not nilpotent. And secondly, consider space subset R of H or from H such that add H on V non-degenerate. Okay. Where? Alpha plus beta. Yes, sure. Okay. So consider these two sets. I claim that these two sets are open in the Riesky topology. Let's recall that the Riesky topology closed sets are not all unions of zeros of polynomials, right? If it's completion of some sets of zeros of polynomials, then it is open. Okay, first, why this is open? Maybe it's simpler. What does it mean that add H on V is degenerate? It means that determinant is equal to 0. Non-degenerate, it means that determinant is non-zero. Determinant is some polynomial function on H. So we choose basis. Therefore, this is a Riesky open. Right? What? Yeah. In space, so we have H. The Riesky topology in H is vector space. We have the Riesky topology on H. What about this? Why, if add H is not nilpotent, then it is a Riesky open? Do you know some? What does it mean that your operator is nilpotent? Some operator is nilpotent. Zeros. So it means that it's some polynomial condition. So if it is not nilpotent, what does it mean? Okay, it's just completion to the set that all zeros. So you can consider all other things, and it's open, and it's our set U. Okay, these are the Riesky open sets, but unfortunately, and what you know, so there is some claim about the Riesky open sets that intersection of any two the Riesky open sets is non-empty. Probably you heard it. So let's say claim, so exercise, or well known, if U be the Riesky open and non-empty, empty is also open, it follows that their intersection is also non-empty. It's very, very different from ordinary topology. Okay. Then these are two the Riesky open sets. Let's prove that they are non-empty. Then they will have non-zero intersection. First of all, I claim that R is non-empty. Why? Do you know some element in R? A. By definition of A is element of R. So therefore, R is non-empty, the Riesky open set. So what we want to say about U? If U is non-empty, so we want to prove that H is nilpotent. It is the same as to prove that U is empty, right? If U is empty, then for any H from H, add H is nilpotent. so it's by Engel's theorem, it's nilpotent. So it's enough to prove that this guy is empty. Suppose that U is non-empty. Then we have some element inside U and R. There exists H, there exists some B in U intersect R. And what we know that R adjoint B on H is non-nilpotent. So, okay, we have these properties. And we know that adjoint B on V is right. Very good. So then consider, so this element has its own decomposition like this. With any element you can consider decomposition. What you could say about G0B in this case? How it's related with this decomposition with respect to A? If we know that at B on all non-zero it's invertible, and for 0 it's non-nilpotent. So what does it mean? So G0B is just some subset of G0A plus plus lambda is not equal to 0, G lambda A. Could some element from here be in G0B? What is G0B? It means that add B, so it's generalized Eugen space to the B. So add B to the power n is 0 on this element. But it is possible. It is not possible because add is invertible on this space. If you have some vector which contains some component from there, it is impossible to be 0. Therefore, it's inside G0A. But probably it could coincide. Could it coincide with G0A? It's non-nilpotent. What does it mean? So G0A is exactly so G0. So now we see that therefore it follows that G0B is inside G0A. But we use this fact. How can we use this fact? Could be if G0B is equal to G0A. What does it mean? So it means that so G0A is just like kernel of add A to the some big power n, right? So to some power n by definition. And we know something. We know that add could it be kernel of add A to the power n? So if G0A is equal to G0B, add B is non-nilpotent, so we do not have any degree of B such that it is 0 operator on your space. Like add B to the power n is not identically equal to 0 for any on where? On G0A. H is G0A for any n. Is there some contradiction? So we have some vector space. We have some operator which is n degree is non-zero. G0B by definition is what? It's just kernel of add B to some power. Right? Then it's necessarily smaller. Okay. Why? So we know that it cannot contain this component, so it should be inside here. But here it cannot, so it cannot coincide with entire space because it's a non-nilpotent operator on this space. It's just some space with non-nilpotent operator. Then if you consider its decomposition in this space, then it can't coincide with the entire space. So therefore it follows that G0b, so this is not important. This is important. Non-nilpotent operator on some space cannot coincide. Its kernel. So this is kernel. This is important for some n. So then it is not entire space. Okay. Like the space is the same. Like it's the same as we act. We act by Ilyin algebra on itself. So G0b is some proper subalgebra in G0a. But now I want, probably I should, here, let's say, okay, claim Cartan subalgebra. Cartan subalgebra is no, sorry, I don't, sorry, it's different. Okay, now we see that G0b is G0a, but it can't be like this. Why? What is contradiction? We should use that our element is regular, right? Let's recall that A is regular element. So it means that CR of X is non-zero. What is dimension of G0? So what you could say about dimension of G0b is less than dimension of G0a. But what is dimension of G0b in terms of polynomial, characteristic polynomial? What is dimension of G0b? Let me write and let's see. So I claim that it is least number m such that Cm of b is non-equal to 0. So dimension of generalized eigenspace for G0 is least number such that Cm of b is non-zero. Why? So these numbers are just already erased. So we have right. How to relate dimension of G0b and something about characteristic polynomial at b. So it is kernel, let's record it's kernel of at b to the power n for some n. Yes. So you have some linear operator. Its dimension of generalized eigenspace corresponding to 0. So here you have some, okay, minus lambda to the d plus so on. We claim that, okay, here you have Cm of b minus lambda to d minus m, and all others should be 0. Why? And this is non-zero. But why? Yeah, that's
because if we consider composition,
yes.
then we substitute minus lambda, and then
So you mean, you're right, yeah, you mean that consider the matrix of this operator, right? It will be some number of zeros, right? And something else, Jordan normal form. And you compute determinant of such matrix. So it's exactly has this form. So this is just linear algebra. But it's contradiction. It cannot be like this because it's rank. You cannot have, by definition of rank, it's least coefficient such that it is non-zero on some element. So it's contradiction. Okay, so it's not complete the proof. So what we get? So we get that U is empty. We have proved. So it implies that H is nilpotent. Okay. Now we need to prove that it coincides with this normalizer. Oh, okay. So if B belongs to normalizer of H, so it means that BH is inside H. It means that like B inside H, right? Because A belongs to H, we know. Let's recall that A is our regular element. It's different B. Okay, let's use C. Sorry, it's not B we use here. It's just some arbitrary element of normalizer. So CA belongs H. So it follows that add A on H is what we can say about operator add A on H. Is nilpotent, right? It's because nilpotently algebra is nilpotent. Therefore, we know that add A to some big power, like say n of B is equal to 0 of C. Sorry, right? It's nilpotent operator of H. CA belongs to H, so add A to the power n plus 1 if you want, right? It's equal to 0, but it means it implies that C belongs to what? To G0A. C belongs to H. Okay? So that's obvious. So we have proved that it is indeed self-normalized, so it's Cartan subalgebra. So we choose any regular element and we get Cartan subalgebra. Any questions? Okay, consider some element of normalizer. Then for any H from H, CH belongs to H. So it means that CA belongs to H. A is our element. We can H, let's recall that H is G0A. Belongs to H. So what we know that add A on H is nilpotent. It follows that add A to the power n on C is 0 for some n. Because AC belongs to H, add A to the power n is 0. Okay, it's better, maybe n plus 1. So C belongs to H by definition of H. So we consider any element from normalizer and see that it belongs to H. So normalizer is equal to H. G0A is just, let's recall it, it's kernel of add A to the power n. Because by definition. Okay, so very good. Now what else? Already did one page. Very good. Let's recall this. Okay, let's recall here. We want to prove, and probably we'll prove then next time. But now let's consider. let's discuss some consequences of it. We already discussed that its consequences that root system. We have map from semi-simple algebras to root systems, but some others. So theorem again. Recall any two Cartan subalgebras are conjugated. Okay. Corollary 1. Okay. We have, let me formulate it explicitly. We have map from semi-simple algebras to root systems. Secondly, any Cartan subalgebra, so it means that in semi-simple case, any maximum toric subalgebra, any Cartan subalgebra has form G0A for some A from G. And all Cartan subalgebras are isomorphic. So I claim that any, so it's obvious, right? To what we know, consider any Cartan subalgebra, consider some regular element, consider such algebra. It's also Cartan subalgebra. They conjugated, so it means that it's sigma of G0A. But what you do? But we already computed it. What is G? Not computed, but okay, we computed for Eugen spaces. But what do you think? What is sigma of G0A? It is G0 sigma of A, so it's easy to check, as we did for G0 sigma of A. By this theorem, we didn't prove it. It's corollary for soft theorem. If any two Cartan subalgebras conjugated, let's choose A. Let's say A regular. Then we know that this is Cartan subalgebra to this. But if you conjugate this, you get G0 sigma of A more plus sigma of A is regular. So yeah, from beginning we assumed that A is regular. A is regular, then G0 of A is Cartan, then you have some map from Yo to Cartan, but sigma of G0A is G0 of sigma of A, and sigma of A is also regular. Well, maybe it's not. Why? Because it's automorphism of your algebra. It maps regular elements to regular elements, obviously. But it's not. I think it's enough, right? Sigma of G0 of A is G0 of sigma of A, and it is equal to H. So H is equal to G0 of sigma of A. But sigma of A is regular. I want to say that indeed it also has form G0 of A. Yeah. So any Cartan subalgebra has form G0 of A. So any maximal toric subalgebra has this form. In fact, there is another definition of it. Okay, next time we will discuss it. Simpler. It could be just centralizer, not generalized Eugen space. Yeah. So we have 5 minutes. What I can say about proof of theorem? Okay, let me give scheme of the proof. Proof is again simple. It use some So in order to prove it, we need to use two lemmas, two propositions. Proposition 1 is as the following: if H from G is nilpotent subalgebra, then we have decomposition, and then G is direct sum of G lambda H, where lambda from H star, okay, and G lambda FH is kernel of add H minus lambda of H e to some big number n, and some number n. Okay. It depends on what? It depends on on lambda, n of lambda. What is the claim? So it's like the claim is that if you have nilpotent subalgebra with Ilyin algebra, you can also consider root decomposition. It's not surprising because like our maximal toric subalgebras are Cartan subalgebras. Cartan subalgebras are nilpotent subalgebras. The claim is that there is general procedure that you can, if you have nilpotent subalgebra, you also have something like root decomposition. And it has a little bit different nature because for semi-simple case you consider just you have the set of semi-simple commuting elements and you consider the common eigenspace decomposition. Here it will be here it will be a little bit worse. It will be common generalized eigenspace decomposition. So, but moreover, and if H is Cartan, then G0 of G0 H is equal to H. So it's very similar to what we consider for maximal toric subalgebras. Then secondly, proposition 2 is as follows. Is from the Zariski topology. If you have some map from Cn, it's really for any field, Kn to Km, polynomial map, and there exists point from Kn such that differential at this point is non-degenerate, then it implies that image IMF contains U is the Zariski open set. Non-empty. If you have polynomial map, over complex, okay, let's see. It's important that the field should be algebraically closed. If you have polynomial map for algebraically closed field, such that differential is non-singular, at least at one point, then image contains contains the Zariski open set. If we have this, so this is some lemma, then the proof proceeds as follows. I can say it in 3 minutes. So we have Cartan subalgebra H. We have decomposition of H plus GH lambda from H star. And let's choose some basis of these guys. So for any x from G can be represented as x is equal to some H from H plus some xi ei from 1 to some number by I. Okay. So let's just choose some basis here, and you can represent any element in this form. And then I want to consider the following map, like in this lemma. I want to consider map f of f from G to G, which is given by the following: f of x is equal to e to the power add x1 plus e to the, so add x1 okay, add e1 x1 to e to add e2 x2 e to the power add en xn to h. I will consider such map. So in order to define it, I need to prove that for any, so it's additional, for any add x is nilpotent. So I need to prove this. It follows from some consideration with these generalized eigenspaces. Then I can define this map. It will be my map like this. Then I want to compute differential of this map, and I will show that it is non-degenerate at some point. It will fall. So I want to show that it is non-degenerate at some point. And then what? Then you could consider image of this map. If you have let's consider it works for any Cartan subalgebra. So suppose you have Cartan subalgebra H1, you have Cartan subalgebra H2, H1. So this map, it maps from G to G, but in fact it maps from H to G, right? So okay, it maps from H to G. So you have some set omega H non-empty, the risky open set of G. And it is just some subset of conjugated elements of H1. So we have this map. I claim that this proposition applies to this map. You can find some point. Then you could consider H1 and you will consider f of H1. Not f of H1, so f of, I mean, you have fH1, okay? You have fH2. You could consider fH1 of G, fH2 of G, okay? This will be some omega H1. This, so it contains some non-empty the risky open set omega H1. It contains some non-empty the risky open subset omega H2, right? And I want to consider third space of regular elements. So it's a subset of G. And it's also, you have the risky open subsets of G. And you have omega R set of regular elements. Okay? And it also the risky open. Like it's by definition. Then you have non-empty section of all these three guys. Right? Okay, therefore there exists H, X from G1, such that X is equal to sigma, to some sigma. So you act by elements of your group. There exists a sigma 1 and sigma 2 from G. Sigma of H1 is equal to sigma of H2. Okay? Right? So there exists X from G, H1 from H1, H2 from H2, sigma 1, sigma 2 from G, such that this. So it means that we have non-empty intersection of all these three sets. Then what I can, then H1 is sigma minus 1 of X, is regular. Because our map, what is map? You apply some element of a group to element of Cartan subalgebra. It's by definition of this map. It's regular, but as a last proposition I need is also simple. If you have some regular H from H is regular, then your Cartan subalgebra coincides with this G0H for this element. If you could find in your Cartan subalgebra regular element, then this generalized tangent space for this element, it's exactly your Cartan subalgebra. Then it follows. Therefore we see that H1 is equal to G0 of H1, and H2 is equal to G0 of H2. Okay. But then if you consider sigma is equal to sigma 2 minus 1 sigma 1, then it maps exactly H1 to H2. Because as we said, if sigma of G0A is G0 of sigma of A. So it maps to X, and then so it maps H1 to X, it maps or inverse. So then firstly we map H1 to X, it's sigma 1, it's sigma 2. I think it's like this. Sorry. So we map H1 to X and then map X to H2. So we have, and by this we have found enrollment. Okay, we will do it next time in details with everything. But I want to show that it's pretty simple. We know that any Cartan so we can show that that any Cartan subalgebra is just this, and then just it follows. Okay, let's have a break for 10 minutes.